Okay, welcome to E222. From this week, things are going to get more complicated, and basically we're going to move into more of a real deal sort of situation. What we start off with today is called sequential logic. Okay, sequential logic. Now, just to highlight the difference between sequential logic and combinational logic. In combinational logic, it's all one-way traffic, right? For example, you've done the labs, you've done so many tutorials, so many different sorts of problems that when you have a particular set of inputs, there is a definite output, right? There is a definite output, okay? For a particular set of inputs, so let's say if you have a adder circuit, if you have a 1 and 1, two ones going into your half adder, definitely your output will be 0 for your sum and 1 for your carry. Yeah? Straightforward. No two ways about it. Right? So generally what we see is, or if you take any other circuit, let's say for example that security system, right? Which we did for our midterm exam. We discussed the solution last week Thursday. Yes, for the security system, if let's say sensor A, B and C are 0 and only sensor D is 1, the output light will be off for sure. There's no two ways about it. So in a combinational system, in combinational logic, the bits, they flow in one direction and it's a fixed result. The result is fixed according to the design of your circuit. The result is fixed according to the design of your circuit. Whether you're using a multiplexer or decoder or adder or subtractor, or you made your own big circuit like the security system which you did based on NO or OR-N, whatever or NAND, the results will be fixed according to the truth table. Right. Now in combinational circuits, combinational circuits, some of the examples were at a higher level, we made a mux, a multiplexer, demultiplexer, encoder, decoder. We made an adder, half subtractor, full adder, full subtractor. You made a sum of product circuit, depending on your sum of product circuit or minimized sum of product circuit. You made your product of sum circuit, your min term circuit, your max term circuit on NO, or you can even do it in NAND. You've done all of this, right? Okay, now we move to combinational. In combinational circuit, there is some feedback. Now, by now, in E212, what topic are you covering in E212 right now? Are you doing amplifiers or are you doing op-amps, operational amplifiers already? No, not yet. Amplifiers, which one? BJT amplifiers or FET amplifiers? FET amplifiers, all right. Now, one of the key points is there is something known as feedback. Let me show you what feedback is. Let me show you a circuit, and that's the circuit which we will look at today. Now, guys, I'm happy that you are here, and basically by being here, you have gone a long way in helping yourself. Okay, guys, have a look at this circuit here. I just want to show you one particular circuit, right? I want you to notice this part, the highlighted part. And we're going to work this circuit out. Okay, let's all right, so okay. Okay, guys, have a look at this circuit here. Pay attention to the circuit. Look at how there's feedback. Can you see the output? The output line is being fed into the input. Yeah? The output line from one side is being taken into the input. Yeah? So you're taking some information from the output and feeding it back into the input. That's what you call a feedback system. Now later on, in fact, all engineering systems, not your studies, I'm talking about your system, right? Even in real life is based on feedback. Let's say for example, if I start speaking without any mic, and then you will tell me, you will give information back saying that, hey, we can't hear you, can you increase the volume? So what will I do? I'll bring the mic closer. So what are you giving me essentially, right? So if I start speaking without the mic, you won't be able to hear me, and you'll say, hey, we can't hear you, right? So you'll say, hey, can you bring the mic closer, or can you increase the volume? What you're giving me is feedback. So the output, you guys are returning information back to the input, right? You're returning information back to the input, and then I am taking action. So via this circuit, we'll study this circuit shortly, right? And similarly, you know, like for example, I don't know if it's already on your Moodle shell. It's something called the closed loop survey, or something along those lines. Please, I would encourage you to take part in that survey, because that helps me. Somewhere over here, student feedback, closing the loop, right? If you see that link over there, student feedback, closing the loop 2019, go inside, and it's just a few multiple choice questions, and give me feedback so that I can improve myself, right? So I'm asking you for feedback. At the end of the semester, every semester, you guys get a chance to do some feedback survey, evaluation of courses. Oh, I didn't like the lecturer's shirt, I didn't like his shoes, you know, or, you know, I didn't like his voice, or something like that, right? Okay, so you can give feedback. You can give feedback, or you can say, oh yeah, I like the color of his pen, all right? So, yeah, that's all right, that's good. You give information, you know, which improves the course. So similarly, there's this feedback opportunity for you to do via this feedback. This is what they call the halfway feedback. I'm not eligible to take the questionnaire because I'm the lecturer, but you are eligible to take that questionnaire because you are the student. All right, guys. So let's now look at this circuit. Let's go step by step, look at this circuit. It's very hot over here in front because I don't know why these lights are on. Anyway, let's do this circuit, guys. Have a look at that. If you want, go ahead and draw that circuit. I'll give you a chance to draw that circuit. Go ahead and draw that circuit. And that will be letter S. Okay, we've got to do this the old school way. Usually I don't like writing notes and in class and all that, but hey, some things you've got to do step by step. Okay, so can you draw that circuit? Can you see there's an S and an R, and those are two NAND gates. There are two NAND gates. Everyone done? Simple system. Can you see how the output is fed back? Right? Okay. Right. Next, I want you to write out the, can you do the truth table for a NAND gate? Truth table for a simple NAND gate, two input NAND gate. Okay, I'm flipping over, so you got this circuit. I'm flipping over to the document camera now. That's our circuit. By the way, guys, the name of this circuit is the SR Latch. Now, let me give you the application of this circuit beforehand. And it's all in the notes. these sequential circuits, the main point is this. They have memory. They have memory. Like for example, if you take your decoder circuit or encoder circuit, or if you take your security camera circuit, the one which we did, the security light circuit which we did in our midterm exam, the solution I showed you on Thursday last week. Or if you take your mux circuit, the one which you did in your lab last week, or if you take your any of the circuits, combinational circuits, the moment you change your input, the output changes. You change your input, the output changes. Now, sequential circuits have memory. That's the key part. Sequential circuits have memory. All right? Just remember that. Combinational circuits, the moment you change your input, it will process your input, right, according to the new set of inputs, and it will bring you an output, right? Sometimes if you have a 16 line truth table, yes. Let's say, for example, let's do the security problem. Let's say if you had A, B, and C as 0 and D as 1, your output will be 0. And if you had A, B as 0, B as 1, C as 1, and D as 0. So again, your output will be 0. But your input changed, and you're saying, hey, those two lines, the answer is the same. Yes, the answer is the same. It's still giving a 0 because majority input was 0, right? But that processing, it did a fresh new calculation in order to come to the answer 0. It didn't save it in memory and remember that it was 0. Now, for sequential circuits, they remember. Because of the feedback loop, right, they are able to, they have this new capability of remembering, right? It's just like you are, let's say your vehicle looks like a tricycle. Do you remember Mr. Bean? Mr. Bean, has anyone watched Mr. Bean? It's good, it's very educational. All right, okay. And sometimes one of these guys he doesn't like is this vehicle he rides and it's got 3 tires. Not he rides. One of his friends or somebody rides it and he always pushes him over and the other guy always falls down or something. So let us say you have you build a tricycle. Let's say you'd build a tricycle, right, for your fast vehicle to travel to uni, right, from Nassori to Suva every morning. You have a motorized electric tricycle, right? But the problem with the electric tricycle is you're always flipping over. You're always falling down on sharp bends, right? That's because there is a design flaw. The moment you have 4 wheels now on your system, your other friend, he makes not a bicycle, he makes 4-wheel system, 4-wheel electric vehicle, still on a simple structure like a tricycle, but with 4 wheels. And you notice that his 4-wheel vehicle does not flip over on sharp bends. Why? It's the nature of the design. Similarly, until we were doing combinational, all the bits are flowing in one direction, there's no memory. The moment you started feeding back the bits back into input like this, hey, suddenly there is memory. All right, that's the key difference. Now, this is the SR Latch. It is the basic building block. It is what you call the DNA of sequential systems. And once you know sequential, you know memory. Once you know memory, you can build large systems. Like, for example, a calculator, you can't just build a calculator based on just doing addition and subtraction. You have to have some memory. The result has to go and store somewhere, all right? Then you can do some large calculations. So you can do 1 plus 3 plus, 15 plus 26 plus 45, all right? So when you add the 3 numbers, because the answer is continually being stored in memory, you can do some large calculations, all right? Or if you're doing a clock can only move forward if it can remember what the previous, right? So if it was minute number 3 now, after 60 seconds, the clock is supposed to show minute number 4, only if it can remember what it was in the previous minute. All right, now, this is the basic building block. This is the SR Latch, right? That's the name. It's the basic building block. It is the DNA. It's like the basic cell. If you don't understand this today, and did you receive a message on your Viber or something to come to lectures today? All right? If you don't understand this today, you're going to get left behind. And unfortunately for your friends, they're going to suffer now. All right, okay. All right, okay. So let's have a look at just on a sideline basis. for our NAND, oh, spelling mistake, NAND, so let's say input A, input B, input Z, right? 0, 0, 0, 1, 1, 0, 1, 1, just for our NAND, right? This is some side information just to help us, right, do some calculations, all right? 0 NAND 0, guys, 0 NAND 0 will give you a 1, right? 0 NAND 0 will give you a 1. 0 NAND 1 will give you a 1. 1 NAND 0, 1. 1 NAND 1, 0. Now, one key observation over here, guys. One key observation. The key observation is that if you have a NAND gate, what can you tell me? What can be one of the inputs such that the output will remain 1? What should one of the inputs be so that the output remains fixed? If you look at it, the moment one of the inputs is a 0, yeah? The moment one of the inputs is a 0, it doesn't really matter what your other input is. X, don't care, right? It doesn't really matter what your other input is. Your output will always be 1, okay? All right? So this is a key piece of information in order to understand our latch. The latch is the basic building block, and we're going to repeat it again. All right? We're going to do two things today. We're going to do the SR latch, then we'll do the SR flip-flop. Okay, there's something else called the flip-flop. All right. Okay. Okay, so everyone happy with the NAND gate explanation? No matter what your second input will be, the moment one input is a 0, they say, you know, output will be 1. Okay? It will be fixed to 1. Is that everyone happy with that? Okay, this is a very crucial point over here. Okay, now from the combinational world, we move to the sequential world. Okay. Now let's draw up our table. There are two inputs into this circuit. There are two inputs into this circuit. So I'm going to take you not in the normal sequence. Okay, so that's S, that's R. And how many outputs, guys? That's Q. That's Q bar. Yeah? How many outputs? There are two outputs, Q and Q bar. Hey, by the way, just by looking at the name of Q and Q bar, what are we trying to say over here? Just by looking at the name. How we've labeled the two outputs. One output is Q, the other output is Q bar, which means what? That they are both opposites of each other. If Q is 0, Q bar will be 1. And if Q is 1, Q bar will be 0. If Q bar is 1, Q will be 0. And if Q bar is 0, Q will be 1. So those two have got to be opposites. That's our design. We want our circuit to be designed in that way. All right. Now we have to look at the scenarios. This is the thing about this particular circuit, right? Scenario. Okay. I don't know if I've got the spelling right for scenario. Scenario. Okay, just check that. Okay? All right. Okay. Okay, let's take case 1. All right, guys. In case 1, I'm going to feed S with a 0 and R with a 1. Deliberately, I'm doing that, right? I'm not starting off with a 0, 0. I just want to show you how complex this circuit is. Remember, I made a statement early on. Security camera problem, summing circuit, addition, subtraction circuit, mux, demux, you change the input combination, the output changes. You'll watch over here what happens. Okay. 0, 1. How do we handle this, guys? All right, let's come here. Very important. All right. Now let's look at the first flip-flop. I mean, the first NAND gate. That's NAND gate 1, right? Even though this numbering is not important, but I'm just labeling it just to teach you. In your normal circuit, you don't need to label them. All right, S is a 0. S is a 0. But you'll be scratching in your head and saying, hey, but what is the second input into NAND gate number 1? What is the second input into NAND gate number 1? We don't know. Because when we turned on the circuit, we don't know. Right? Okay? How do we handle this situation? Okay, but remember our NAND gate studies. We wrote something early on. The moment, right, one of the inputs into a NAND gate is 0, what is the output? It is a 1. Right? Can you see from this thing here? Remember? If one input is a 0, automatically output will be 1. We don't care what this is. Right? We don't care what the second input is. So, therefore, what will Q be now? Q will be 1. Okay. Now, all right. Now, if Q is a 1, therefore, what is the second input into the R? Can you see this guy is 1? That 1 travels down this way. You can write it with pencil if you want, but we'll be using this circuit so many times that, yeah, you can write it down. So this 1 travels down this way. What is R? R is a 1. So 1 NAND 1 gives you a 0. Now let's see. Is our design, we designed this to say that one output will be Q, the other output will be Q bar. Yeah? We want it to be opposites. So if one partner is male, the other partner is going to be female. They can't be both male. All right? Okay? So one should be Q, the other should be opposite. You can't have the same thing. All right? Q, Q bar. So our design is working. Our design is working. Now, deliberately, I show you the next step. In case 1. We are still doing case 1. Let us try the scenario where immediately after 0, 0, we do 1, 1. Now, I want you to tell me that with case 1, when we did 0, 1, what happened? Q became a 1, right? And obviously Q bar will become 0. If Q is 1, Q bar should become a 0. Q bar should, right? Look at the word I'm using. It should become a 0. I will show you later on, there's 1 or 2 cases where the system rebels against you, right? It rebels against the designer, right? It tries to act out of line, all right? So it should become a 1. So 0, if S is 0, R is 1, Q becomes 1. So we are setting Q. When somebody says set the switch, all right, in digital electronics, if somebody says set the switch, what does that mean? It means set it to 1. Set it, all right? If somebody says reset, you know when you use the thing reset on the stopwatch, if you've got a stopwatch on your mobile phone and you say reset, what does it do? It makes it all 0. Okay, so just remember these 2 words, set and reset. So what have we done? We have set Q, right? We have set the circuit. Now let's try 1, 1. Okay, let's try 1, 1. Now, with 1, 1, but remember, in this case, it's immediately after 0, 1. 0, 1 was a fresh start. 1, 1 is follow up, right? It's not, you cannot use this circuit, that's the other thing. You cannot use these circuits as a fresh start. Only with set and reset, and I'll show you what reset is, you do a fresh start. But over here, with 1, 1, we are doing a follow up, okay? A follow up. All right, let's see what a follow up is. Okay, if S is 1, but hey, what was Q bar? What was Q bar over here? It was already a follow. We're doing a follow-up line, right? What was Q bar? Q bar was already 0, right? Q bar was already 0. So S is 1. We are feeding 1 now. But this is after we've done the 1, 0, 0, 1 over here. After we've done it. So it will remember what our Q bar is. Q bar is still got the number 0. So 1 NAND 0, 1 NAND 0 gives you a 1. Q will now be 1. Yeah? Okay. Everyone got this? S is 1. We are feeding that into the table because we have control. We have full control over what S and R are. Yeah? We have full control over the inputs. But we don't have control over the other inputs, these two inputs. No control over these two, but yes control over these two. Yes, full control, no control. Okay. So where do we get this second one from? It was from the previous line. SR Latch depends on what the previous inputs were as well. Not only current input, but previous inputs. Current input as well as previous inputs. So previous inputs gave you this 1. 1 and 1, okay, that's 1, and then 1 gives you a 1. Right. So that one comes down here. Sorry, that one comes down here. So that becomes a 1, and your R is a 1. And your R is a 1. 1 and 1 gives you 0. I want you to notice something over here, guys. What happened when we did a 1, 1? Okay, with 0, 1, okay, with 0, 1, our Q was set to 1. Q bar obviously is the opposite, becomes 0. And with 1, 1, the output result stays the same. So we are trying to look into something now. There is something happening with 1, 1. Okay, let's try case 2. You'll now start to see what case 2 happens. All right. Case 2. Let us try the opposite. Let us try 1, 0. Fresh start with case 2. Right, fresh start. Okay. This time around, we start off with this 0 over here because we know it's always easier to handle. Right? It's always easier to handle. So let's now feed a 0 over here. If we feed a 0 into this NAND gate, based on our established rule, this Q bar will become a 1. Yeah? Happy everyone? If that's a 1, Q bar, so the second input into the NAND gate will become what? The second input into the NAND gate will become a 1, but our S was a 1. Look at this. Our S was a 1. Yeah? So 1 NAND 1 will give you a 0. So what do we see? Hey, when we had S1, R0, our Q became 0, Q bar became 1. So it is respecting our design. The output is respecting our design. Yeah, 0, 1. Now, immediately after 1, 0, we place a 1, 1. Again, 1, 1. I just want to show you case 2. Right. Immediately after 1, 0, we place a 1, 1. Right. Now, S is a 1. S is a 1. Right. And, okay. Let's see what we know already. Q, right? Q is a 0. Q is a 0. And Q comes down into the second input of the second NAND gate, right? So 0 and R is a 1. 0 NAND 0 will give you a 0 NAND 1 will give you a 1. And let's look at the other one. We know S is a 1. Q bar from before is a 1. 1 NAND 1 will give you a 1 NAND 1 will give you a 0. There we go. Now I want you to see something over here. There's an observation. What pattern do you see? What pattern do you see? Okay, if we plug in a 0, 1, Q becomes 1, Q bar becomes 0. If we plug in a 1, 1, immediately after, 1, 1 is always a follow-up, right? This is the design of our circuit. We made it like that, right? 1, 1 is a follow-up, right? If we plug in a 1, 1 immediately after, it will give you 1, 0 if the previous was 0, 1, yeah? Okay? Right? Can you see in case 1, when 1, 1 was there, what did it give? It gave the same answer as before. It gave the same answer as previously. Now look at case 2. Case 2, we do a 1, 0, your Q is reset, right? And immediately after that, if we plug in a 1, 1, what happens? We have, once again, the same answer as before. So can you see, in this same circuit, we've got two scenarios. 1, 1 earlier on was giving an answer of 1, 0. And 1, 1 now, in case 2, is giving a answer of 0, 1. 1, 1 is playing a double role over here. It's not giving the same answer, right? It's giving the answer of what was before. Therefore, what is 1, 1? 1, 1 is memory. What have you achieved? You've achieved memory. Okay? So 1, 0 and 0, 1, the first lines of case 1 and case 2 is plugging in the bit. We just have to save one bit, right? This circuit just does one bit. It's plugging in the bit into the memory, like it's an empty jar, and we're plugging in, oh, make this 1, right? And 1, 1 saves it into memory. Okay? All right? It shows you whatever was there before, right? What was there before? Like, for example, in your calculator, there's memory recall. Do you remember that memory recall? What's in the memory? Memory recall. So 1, 1 does memory recall. It shows you the answer of the previous command. The previous command was either 0, 1 or 1, 0. Okay, so if you look at our truth table, there's something still missing, guys. Something still missing. What's missing? If you look at our truth table, something is still missing. Well, 1, 1 is missing. Sorry, 0, 0 is missing. Let's try 0, 0. And you'll see some funny thing over here. Okay? Let's do 0, 0. Wow. Well, if S is 0, if one input is 0, obviously Q should be 1. And if R is 0, Q bar should be 1 as well. Already we have one red flag. According to our design, we would have loved it. It should have been that way, right? It should have been the case that Q is 1 and Q bar should be opposite. It should have been opposites, but already our design is starting to flop. Our design is starting to flop. The circuit design is not going, right? Q and Q bar, error. Okay, there's an error. All right, just for the sake of it, let's go ahead and just do a 1, 1 over here. Let us see if it gives us the same answer or not. Right, let us see if it gives us the same answer or not. All right, so Q was 1, 1, okay, Q is 1. Okay, let's do this. Q bar is 1, Q bar is 1, and S is 1. 1 and 1 gives us a 0. And there's already an issue over here. There's already a clash. So S was 1, right? We knew from the previous line that Q bar is 1. 1 and 1 should give you a 0. And Q, yeah, is giving a 0, but previously it was storing a 1. Okay, now let's try the other one. Q is 1, right? And it comes down here, 1 and 1, Q bar is 0. So what do we see over here, guys? And now this thing goes into an infinite loop. Loop 3, case number 3, goes into an infinite loop. Because if you really look at it, what will it be? What should feed in? If you look at your circuit, in case 3, right, when you have both zeros and then followed by both 1, right, technically our 1, 1 is supposed to be an error, right? So obviously you're already getting an error in line number 1. You're also getting an error in line number 2, because which one do you pick? I want you to go through that in your free time. You might not be able to pick what I'm saying now. Once again, you see your inputs are already 1, 1 over here. The two second inputs, the second inputs. And you are supplying 1, 1. The answer is 0, 0. But over here, the moment it becomes 0, right? But that was already 1. So it's 0 clashing with a 1 over here and 0 clashing with a 1 over here. So it enters into an infinite loop, right? Again, you have error. So there's a situation over here. There is some kind of situation going in case 3. So finally, let's draw our truth table. I'll tell you what we're going to do, how we're going to handle that. SR Q bar 0 0 0 1 1 0 1 1. All right. Now, obviously we've worked out the answer for 0 1. If it is 0 1, it will always give a consistent answer. If it is a 0 1, so this is SR Latch built using NAND gates. All right. Okay, my friends. Now, if you have 0 1, we have a definite answer. What would that be? If you have 0 1, your Q is set, Q bar is 0. If you have 1 0, your Q is reset, your Q bar, oh, that's a bar over here, guys, right? Okay, so that's just a summary of early on. 1 1. 1 1 also gave different answers at different times. But one thing was consistent with 1 1. What was it? It gave the answer of before. So we just write down it had memory. And what do we do with 0 0? That's the naughty one. All right? Okay? What do we do with that? So we just don't go there. We say not used. Right? Okay, the nickname for this guy here is set, not the nickname, the technical name. This is reset and this is hold. Okay, so once again, when we have our latch, we deliberately make sure that S and R, we don't supply a 0 0 to it ever. Okay? So your input sequence into your SR latch should never be a 0 0. Our design should be such. Alright? There should be a bit checker or some comparator checker. Alright? Okay? 0 1 will always give a stagnant answer. 0 1 will always give 1 0. And if SR is 1 0, your QQ bar will be 0. That will always give a stagnant answer. 1 1, the condition for 1 1 is it's got to be a follow-up. It can't be the first command. 1 1 cannot be the first command. Maybe you want to make an asterisk and put just a small note over there. 1 1 cannot be the first command. 1 1 can only be a follow-up command of either set or reset. It can follow up from 0 1 or 1 0. But you can't take it in raw with this circuit. This is not a combinational circuit. It's a sequential circuit. Sequential circuits, they don't abide by the rules of combinational. They don't abide by the same rules. All right? And 0 0, so 3 notes you're going to make. For 1 1, it cannot be a fresh command. You can't just turn on your SR latch and place a 1 1. It will only show you if there was some static electricity and all that. It will just show you whatever it was there before. Right? 1 1 cannot be a fresh startup, cannot be the first input. 1 1 is a follow-up input of either 0 1, which is in brackets set, or 1 0, which is in brackets reset. Why do we use the word set? Because Q becomes 1. Reset because Q becomes 0. Alright? Okay, and the third note is 0 0 can never be used, whether in the beginning or in the end or in the middle. You cannot use a 0 0 in this circuit. So this truth table, even though you have 4 possible combinations, only 3 are in use. The fourth one, we don't touch it because it will start to confuse the circuit. Right? If you want to use the circuit effectively, it's just like, guys, it's just like when you are driving, you never press the brake and the accelerator together, right? It's just going against it. It will work. The brake will try to brake and the accelerator will try to rev the engine, right? But you will damage the system. You will damage the system. So we don't do that. Certain things we know. This is the design of the system, that you don't do brake and accelerator together, right? Unless, no, you can't do that, yeah. You can't, yeah. All right, okay. So let's now look at the next circuit. That was the basic building block. Any questions, guys? Questions? I'm going to move one step now, one step higher. Everyone okay? All right, we've got about 10 minutes. I'm going to draw the circuit, at least. Now, let's take our original circuit. And now, this circuit is called the SR Flipflop. By the way, in CS211, have you guys studied Flipflop? No? Yes? CS211? Flipflop? No? Okay, all right. Let's do this circuit. Now, I just wanted you to note over here. Have a look at this block. What can you tell me, guys? About that block. What does that look like? What's sitting inside? That's our SR latch. Now, let me add some more things to this. Okay, that's our circuit. That's Q bar. Let's call this S. That's R, and there's a new line called clock. All right. Q bar and clock. Set. Everyone happy? Oh, you be careful with saying the word set, you know, because set would mean something in technical, in terms of our sequential logic. Okay, is that good? All right. Okay. Okay. Right. So there's a clock. Now, let me introduce you to this circuit. Now, remember your basic building block, the original circuit. The original circuit. That's sitting inside there. Okay, it's flown off. Okay, that's sitting inside over there. Okay, so original SR latch, the latch, you know what the word latch means, right? Latch means, you know, when you have your kitchen cabinet or something and then you close the door and then it goes and holds it in place. Latch, to latch onto something, right? So to hold it in place. So that's our original SR latch. Original SR latch. Okay. Now, for the sake of it, to make life easier, let's call this point here, that point, S star, and that point there, R star. All right. Now, we've got our latch, and S star is feeding into the latch, and R star, S star, R star is feeding into the latch, right? Now, over here on the exterior, you've got a new S, you've got a new R, and you've got something called the clock. Now, why is clock important? You see, in the previous circuit, when you have memory, you need to clock your memory. You can't just say, you know, what do you remember? Or what is the particular status of this circuit outright like that. You've got to ask what is the status of this circuit at this particular time. So we now have a control input. Clock is used to control when the circuit would take in information, right? When it would log in information, right? So basically, for example, when you want to store memory in your particular calculator, the calculator is a very good example. Let's say you want to store the memory 5.14. You've got to press memory M in, yeah? Or is it memory in or memory, how do you store? What do you use? There's probably a button over there which you press to store whatever answer there is into the memory. What is that button in your calculator, FX82? What is it? Sorry? Set. Shift RCL. And that saves it. And what about the other one? Memory? Oh, okay. Okay, it says Shift RCL. So Shift RCL is a button to store into your memory. All right? Shift RCL. So what are you doing? At that point in time, whatever is available, that's what you are storing. Okay? Now, that's what clock does. Clock gives us control over the circuit. The latch, even though it is capable of having memory, but there's no control. There's no control as to when to take the memory. You want to press a button saying now, stop, like stopwatch. You want to press stop or, you know, lap now. Okay? So the clock line is a control line. So basically what we've done is the moment you add clock, which is control, right, into your circuit, what happens? You now have a flip-flop. Okay? A flip-flop. Right? Okay, a flip-flop is a circuit which is able to store one bit of information, but with your control. You instruct it saying, okay, save now, or recall now. When do you want to recall? You press the recall button. Recall now, okay? All right, now let's do the truth table. Okay, so you have clock, you have S, you have R, you have S star. This is not an output, this is intermediate. This is R star. Okay. You have Q and Q bar. Okay. All right. Now, the first point before we knock off for today